What's up, Coder? Welcome back to another data structures and algorithms video. I'm Elizabeth, and today we're going to be continuing the series all about interview patterns, specifically the sliding window pattern. I really love this pattern because, and I know I say I really love everything, but oh my God, my dad is like that. Man, I think I'm becoming my dad. Lots of revelations here on the CoderBite YouTube channel, everybody. Anyway, I do really like this pattern because I think it's the reason why it's such a valuable pattern is because it accomplishes exactly what you might want to accomplish naively with an algorithm or a problem, but it optimizes, and it's kind of like a hack, right? It's like, oh, I could do it this long way, but there's a better way that saves a bunch of time complexity. So I think this is a really cool pattern because it really does kind of level up your answer. And it's pretty prevalent. I think a lot of different interview problems use this pattern. This is the underlying pattern that people want you to use to solve. So today we have another one, another problem for everybody. And yeah, let's stop talking and get into the actual learning. Let's go. Okay, so let's start off with a review of what the sliding window pattern is. And I definitely, if you're new here or you haven't seen the first video in this series, I strongly recommend you go to the introductory video that we did a couple weeks ago, all about the sliding window pattern, with kind of like an easier problem demonstrating the sliding window pattern. But a brief kind of review of what it is. In many problems involving an array or a linked list, we are asked to calculate something among the subarrays of a given size or some variable size. And often these subarrays overlap. There's some duplicative work that happens as you're looking at the different subarrays in the larger array. Often we can use a sliding window to discern what might be overlapping between subarrays and not actually have to do that computation twice. And using the sliding window can help us minimize how many computations we're doing and ultimately save on time complexity. So the sliding window refers to what subarray you're looking at any given point, and then we can grow or shrink the window depending on the problem and how we want to move about the main array. So that's kind of the basics of the sliding window pattern. And as usual, I think that actually coding out different problems does illustrate the pattern better than words do. So let's get into this week's problem. Given an array of positive numbers and a positive number s, sum, find the length of the smallest contiguous subarray whose sum is greater than or equal to s. Return 0 if no such subarray exists. Okay, so first let's define some of these big words because we didn't all become software engineers because we know big words. Let's be honest here. Contiguous. So in this problem, and I think also in general, contiguous means that we are looking at subarrays that are touching, right? It's not this number, and then this other number at the end. It's numbers that are touching will make up these smaller subarrays in the larger subarray. So let's look at an example. Here's an example. We have an array of, some integers, 1, 3, 2, 2, 4, and 5, and then s is equal to 6. So the problem is asking, find the smallest contiguous subarray and the length of that small contiguous subarray, the smallest contiguous subarray, whose sum equals s, or is greater than or equal to s. So how might we do that? So you can go through this just by looking at it, right? And right off the bat, you see that there's a small contiguous subarray, 1, 3, and 2. So that 1 plus 3 plus 2 equals 6. So this small contiguous subarray equals 6. But is it the smallest contiguous subarray? It is not, because right here there is a 2 and a 4. And so that also equals 6 and only has 2 elements as opposed to 3. So that would be the actual smallest contiguous subarray. And I think it's important to note also here that although there is also 5 and 1, that would not be considered contiguous. So depending on the problem, right, this problem specifically is saying that it needs to be contiguous, aka touching, Another problem might count that as not contiguous, but an adequate answer. But this one does not. So let's look at the answer. The answer is, of course, this subarray 2, 4, and the length of that is 2. So our answer would either return 2 or, whatever, you get the idea. So what's our approach here? How are we actually going to solve this? And how are we going to solve it with a sliding window? So what is the sliding window approach here? Let's take a look at, the example we had in the previous slide. So we have 1, 3, 2, 2, 4, 5, and our sum is equal to 6, right? That's the S that we're looking for. And we're looking for the smallest contiguous subarray whose sum is equal to or greater than S, which is 6 in this case. So for this algorithm, there are going to be a few different variables that we initialize right off the bat. So first we have S equals 6, which is passed to us. And then we're going to basically define our window here. And so we have right off the bat, we have our window start, which starts at 0, our window end, which starts at 0, our window sum, which starts at 0, and our minimum length so far, which here is null. So we don't have a minimum length so far. So right off the bat, we've initialized our starting window is going to be, it starts at 0 and it ends at 0. And the only thing in the window is this 1, right? So the first thing we do is we add whatever's in the window to the window sum. So in this case, we're going to add 1 to the window sum, which was 0. And now we have a window sum of 1. So the algorithm goes as follows. Essentially, we want to, with every step of our, window growing or shrinking, we want to check, do all of the elements in the window, are they greater than or equal to S? And if they are, we'll do one thing. And if they're not, we're going to do another thing. So I'll show you exactly what we're going to do, but that's kind of the idea. With every single iteration, we're checking, is what's in the window greater than or equal to S? If yes, do one thing. If no, do another thing. So the question is, what are those things that we do here? So in this case, the answer is no, right? 1 is not greater than or equal to S. So what do? We grow our window. We say, okay, we don't have it yet. Let's see what happens when we add the next element to our window. And that's exactly what we do. We move, the top arrow here is indicating or representing the window end, and then this would be the window start. So we increment window end, right? So we move the arrow, we increment our window end to 1, and then we add everything that is in the window to the window sum, right? So what did we do, right? We have window sum is 1, so now we have to add 3 to our window sum. So now we have a window sum of 4. We ask ourselves again, is 4 equal to or greater than S? No, it's not, right? It's less than. So what do? We increment again, right? We add another element to our window and we increment our window end. So let's see what that does. Okay, so we increment our window end. Now we've slurped 2 into our window. And let's see, so window end is now equal to 2. That's represents the index at which the window is over. And we add 2 to our window sum. So now we have a window sum of 6. Okay, so we finally, right, we've actually achieved it. Our window sum is now equal to or greater than S, right? So we have 6 and 6. So what do we do now? So the first thing we do is we update our minimum length so far to be the current window length. And of course, this is the first one, right? So it's definitely the minimum one so far. But if we had already found one, we would take the minimum of the two values, what we've already found and what we've now discovered, right? But here we're just going to update the minimum length so far, which is now equal to 3, because this is the first contiguous subarray that we found that equals S. And so essentially, now that we have S, the next step is to see, well, we've grown the window, so can we accomplish the same thing by shrinking the window? And that's how we can tell, okay, so we've gotten equal to or greater than S, but now let's see, can we actually start to shrink the window and still have something greater than or equal to S? And that is how you can account for if you've overshot your goal. In this example, we have 6 and 6, so obviously shrinking the window is going to immediately make it too small. But if, let's say, we grew our window and we got 8, and then we could subtract a 1 or 2 from the beginning, we could shrink our window and still accomplish what we want, which is a window sum greater than or equal to S, but with a smaller length, a smaller amount of elements. So let's see what that looks like here. So again, this is the branch of logic that, yes, we did successfully find a contiguous subarray that is greater than or equal to S. So we move the window start. We shrink the window from the beginning. So we move that window start. Window start is now going to be incremented. Even though we're shrinking, we obviously increment the index. And so window start is now 1. And now what do we do with our window sum? We have to subtract, right? We have to take away the element that's no longer in our window. So we take away 1 from our window sum. So now we have 5 as our window sum. And we check again. Is our window sum greater than or equal to 6, right? Greater than or equal to S. It's less than, right? So what do? We grow our window, and so on and so forth. So let's, do it for one more iteration until we get our actual answer. So we grow our window, we increment our window n. So window n is going to become 3 here. We add 2 to our window sum becomes 7. And again, we've reached our case of, yes, this is greater than or equal to S. So what do? We take the minimum of the minimum length so far and the length of our window currently. In this case, it's exactly the same. So minimum length so far is going to stay the same. And we are going to shrink our window again. We're going to attempt to shrink our window. So we increment window start, right? That's how we shrink our window. So window start is now 2. We subtract 3 from our window sum. So now we have 4 as our window sum, which is once again actually less than S. So we have to grow our window, and so on and so forth. But we can continue this example until we get to our final, because we will get a minimum length better than 3, right? So we increment our window end. Window end becomes 4. We add 4 to our window sum, right? So now we have 8, which again, successfully, it's greater than or equal to S, which is 6, but it's 3 once again. So minimum length so far stays the same, even though we have once again accomplished what we wanted to, because we already found one that was 3. So we haven't found a new minimum or a better minimum. But because we have successfully found a sum that is equal to or greater than S, now we can start to shrink our window again, right? And see, can we do better than that with these numbers? So we shrink our window, we increment our window start becomes 3. We subtract 2 from our window sum to, again, represent that the window is shrinking. And we're left with 6, right? And 6 is equal to or greater than S. And so that means that we have now found a better minimum length so far. So our new minimum length so far becomes 2, because we finally found a window that is shorter than what we found so far, that still actually is greater than or equal to S. And our minimum length so far becomes 2, and so on and so forth. So that's essentially how this algorithm works with the growing and the shrinking. And we only ever have to go through the array one time. Window end is never going to loop more than once through the array. And window start at most is going to be looping through just the window size. So, this is a much better algorithm than anything that is looking over all of the permutations of all the possible contiguous subarrays or anything like that. So I love this problem. I think it's like a really fun problem to see visually. And yeah, I think that once you understand the algorithm, the code is actually pretty simple. So let's go over the algorithm in words. This was kind of with a picture, but here's kind of the instruction manual to this problem. So this is a summary of the algorithm. So we initialize window start and window end at the 0th index. We add the value in the window to the window sum. That's where we took that first element, and that was our initial window sum, because that's the smallest possible contiguous subarray, would be just one element. So we start with that first element. We see maybe our S is actually, the first element is equal to or greater than, and then that's the smallest, right? So that's how we start off our algorithm. And then we start to check, is the value greater than or equal to S? And then we have our split in our logic. If yes, if it is greater than or equal to S, we then capture the length of the window in the variable minimum length so far, only if it's smaller than the current minimum length so far, right? And we then shrink the sliding window by decrementing window start. And we repeat from step 3. We check again, is this value greater than or equal to S? So that's kind of just, it's then we continue to iterate, right? So let's go back a little bit. Is the value greater than or equal to S? If no, right, grow the sliding window to the next element by incrementing the window end, right? So that's that, like, looking ahead, adding something to the window. And repeat from step 3, right? Every time you grow the window, you then check again, is this greater than or equal to S? And so it goes. So that's the algorithm. I hope you've been following along so far. And we're going to do this in code, and hopefully it will kind of mirror what we've shown visually and also with words. But I highly recommend you kind of walk through this yourself, play with it a little bit, play with different inputs, and see how this actually does work, and it works very well. Let's get into the code. All right, as per usual, I am in Visual Studio Code, and I just have a completely blank file that we are going to fill with all of this algorithmic deliciousness. That was a weird thing to say, but I think I'm just gonna go with it. Okay, so first things first, of course, let's define some test cases. So I'm just going to console log calling our function, which I guess we could also define, right? Let's say function smallest contiguous subarray. And then what are we going to expect for this array? For this function, I mean. We're going to get an array and an S, right? Okay. So let's say smallest contiguous subarray, and let's pass it the example from the slide. So I'm just going to copy and paste that. So here is that same example from the slides, and here is our S, which is 6. And then I am going to do one more, and I think for this one, I'm going to do a test case that has a single element that is the smallest contiguous subarray that is greater than or equal to S, just to show that it works for that too. So I am going to also copy and paste that from my notes. So that just looks like this, right? And if we make S 7, the smallest contiguous subarray that equals 7 is going to be just 8, right? That will be greater than or equal to 7, despite the fact that there are a lot of other, 5 and 2 make 7, 5, 1, and 2 makes 8, which is greater than 7. So we're going to be testing, does this return 1, right? So those are our two test cases right off the bat, and then here we have our function. So let's go back to our kind of algorithm instructions. And essentially, when you write out an algorithm with words, that's kind of pseudocode, right? Like that, you can kind of think of that as, it's the building blocks to whatever your algorithm is about to become. And I really do strongly suggest doing that before you start to code, because it will help give you some guidelines, and it gives you something, right? If you can pseudocode an algorithm, it's better than not being able to do an algorithm at all. And it also, I personally find that when you have that kind of pseudocode laid out, I am less anxious when I'm actually writing the code, and it feels less like I'm just throwing spaghetti at the wall and seeing what sticks. It's much more like I came in with a plan, I'm trying to accomplish my plan, and it breaks the problem down into smaller subproblems where all you're really ever coding is a single step of the algorithm rather than this giant, function that you're trying to solve and think, and you're doing it all at once. So, even in an interview, it's very, very useful to write it down in simple words first and then kind of code it out. So what did we say? We want to start with some variables, right? So we want a window start, which is 0. We want a window sum, which is also initialized at 0. And then we want the minimum length so far. And I think in the slides I had it as null, right? So that's fine, except we're going to eventually want to be doing a comparison of the minimum length so far and whatever the window size is at any given point in the iteration. And to do the comparison, you need to be doing it with number values, right? To pass into the math.min function that we'll be using to create the new minimum length so far. So instead of initializing it as null, which you can't just pass null to the minimum math.min function, I think I'm going to start it at infinity. And what that does is that any single length that I ever find is going to be less than infinity. So when we pass in the minimum length so far with any window length, the minimum is going to be whatever the actual number value is that we found. It's never going to be infinity. And if we reach the end of the entire array and we've never gotten, if you can't come up with the S out of any of the elements or all of the elements, adding them all together doesn't come close to S or being greater than S. At that point, we can check, is it infinity? If it's infinity, return 0, which if you remember about the problem, that is what we're supposed to return if there are no contiguous subarrays that are greater than or equal to the sum. So I think, that's what we're going to do in code. But essentially, in concept, we're initializing it. It doesn't exist yet. Okay, so we have those, right? And I think for window end, that's the other thing that we kind of talked about in the slides. I think I can just use a for loop to kind of represent that, the window end, because essentially what we're doing is we're iterating through the array until we reach a window sum that is equal to or greater than S. And at that point in that iteration, we start to increment window start to kind of catch up to window end. But window end is just going to continue to iterate just one by one by one. That's going to be the growing of our window. If you didn't understand what I just said, hang tight. We'll actually code it out and you'll see what I mean. So here we have our for loop that we're probably going to use to kind of loop through the array, right? So this is going to be our window end. So that's going to also be initialized at 0. And then while window end is less than the array.length, that should, take us to the end. And then we increment, right? Gotta love a for loop. So basically, this is kind of what's going to be, the for loop is going to do the heavy lifting of growing our window. And then if we ever get to a place where window sum is equal to or greater than S, that's when we're going to start to increment our window start to catch up to our window end. So what do I mean by that? So let's, right off the bat, we have our window start is 0, our window end is 0. What was the first thing we had to do? We had to add an element to the window sum, right? To represent the sum that's in the window so far. So the first thing we do when we're iterating is we want to window sum plus equals the array at the window end, right? And so that's kind of like the slurping of the next element, the growing of the window, right? And then here is where we check, right? So this is the growing of grow the window. And then here's where we have to check, is window sum greater than or equal to S, right? And that's where we're going to do our split here. So essentially, if the window sum is less than S, what do? We grow the window, right? So we do nothing, right? because that means if we do nothing in this iteration, it will just automatically, window end will increment, and then we're going to add the next element to the window sum, and we're going to check again, right? So that's kind of the case of it's not equal to or greater than s. We let the for loop do that heavy lifting for us. And then this line here, that's how we're kind of growing the window. So the only thing we really have to that's left is what do we do if we have found a window sum that is equal to or greater than s. So that's what we'll do right here. And I think we can just start a for loop, or a while loop, right? So this is going to be while the window sum is less than s, right? Because as soon as it's equal to or greater than s, we don't want to shrink the window anymore. We actually want to, the opposite of what I'm saying. While it is greater than or equal to s, what do we want to do? We don't want to grow the window anymore. We actually want to shrink the window, right? Until we are, again, smaller than s, where we want to grow the window. So while it is greater than or equal to s, right? I'm just going to write a couple more comments to try and make this a little clearer. If not, continue the iteration, grow the window, right? Now, if yes, shrink the window until window sum is less than s again, right? And that's when we will continue to grow the window. So I hope that's clear. Okay, so while the window sum is greater than or equal to s, what do we want to do? We want to do a couple things. We want to shrink the window, right? So we want to shrink the window, decrement window start, and remove whatever was at the window start. So remove that first element in window from new shrunken window. I don't know. I hope y'all are following so far. So essentially, those are the things we have to accomplish in this while loop, right? And then we want to do it again and again until finally the window sum is less than s, and we can continue our iteration and start again by growing our window. So what do we have to do here? So we have to first, the first thing we have to do is we have successfully found a window sum that is greater than or equal to s. So we have to capture that the minimum length so far, we have to capture the window length, right? And compare it to the minimum window length that we found so far. So to do that, we can get let current window length equal, and then what we want to do is we want to subtract the window end minus the window start, right? And now remember, this is a length and these are indices. So when we have a window end of 2 and a window start of 0, right, that would be 0th, 1, and 2. The length is 3. So 2 minus 0 is 2. So we have to add 1 to account for the 0-based index. So the current window length will be the window end minus the window start. And then we want to set the minimum length so far to be equal to math.min, the minimum length so far, and the current window length, right? So every time we have a window that has a sum that is greater than or equal to s, we capture that length, and then whichever one is smaller wins, and that's the one that we are left with at the end. Okay, so that's good. Now let's deal with shrinking the window. So to subtract, I think we should do the removing the element first before we increment window start, because then we have window start to just, that's the index that we want to remove. So let's say window sum minus equals the array at window start. Nope, And then, right, so that's removing the element. And then after that, we can just increment our window start. And that's basically it. That's the whole entire algorithm, more or less. So again, this will shrink until we are less than s, and then we will continue to grow, right? Which the only thing that we have to do is add to our window sum, because the for loop is doing the heavy lifting of incrementing and growing our window. Okay, so at the very end of the entire iteration, we are left with, the thing that we want to return, which is that minimum length so far. And then before we return that, we don't want to return infinity, right, in case there was nothing. So we can do a check that if the minimum length so far is equal to infinity, infinity, we can just return 0. So that's where we can, double check that, like, just in case we didn't find anything that it never got to this stage, we only ever grew, right? So that would mean that the window start remained at 0, the window end got to the end of the array, we added all the elements of the array together, and it still wasn't equal to or greater than s. That's what this will represent, right? Otherwise, we can just return that minimum length so far. Let's clean this all up a little bit. And yeah, that's again, it's like once you kind of understand the different branches of logic, it's a relatively easy, straightforward piece of code. Let's see if it works first. Talk a big game, Okay, so let's make this a little lower. Say node. Okay, so we have 2 and 1, which is exactly what we hoped for, right? Because the length of the smallest contiguous subarray that makes 6 is this 4 and the 2. So it's returning the length, which is 2. And then the length of the smallest contiguous subarray for this one that's equal to or greater than 7 is just 1, which is 8. Yeah, so that's the algorithm. And I strongly encourage everybody to walk through this, kind of do a visualization like I did with the arrows, do it with pen and paper alongside the code, use a debugger to kind of walk through step by step how this is actually working. I think the gotchas here are understanding how you're using the for loop to grow the window. Make sure you kind of don't get tripped up there. But yeah, that's all, folks. And there you have it. That's all I got for you guys this week. I think we'll do maybe a couple more of these, maybe 1 or 2 or 3 more problems to kind of really illustrate this pattern and really dive deep. And I would say these problems that we've done so far are more easy, medium problems. And so maybe we'll do some medium hard problems in the coming videos. So if you haven't understood so far, definitely be sure to kind of, again, walk through with a debugger, pen and paper, kind of try and get these concepts really down. But also more problems might help illustrate this further. So definitely look for our next videos coming down the pipeline. Hope everyone's good. I hope everyone is excited about holiday season and, spending some extra time not working, not coding, and just like enjoying, because I think crushing interviews is also, at least there's a small part about it, is being confident, feeling good about yourself, and feeling really happy and just like excited. So definitely make sure you deposit in all of the areas of your life right now. But also keep coming back for more, because we have great stuff coming. Have a good week, everybody. See ya.